pause. Hello everyone, I want to share some news with you about fusion energy. I'm working on new ways to change matter into a clean, non-radioactive energy source. It's a big dream for humanity. We are close to making this dream come true. And because of that, starting July 1st, 2025, in the Czech Republic, under strict punishment, dreaming is forbidden. That's why I always have hairy people and the authorities on my back. If you don't obey, you will be punished. If your dream comes true, you will be punished and your dream taken away. If you leave with your dreams to another country to make them happen, you will be hunted down. If you tell the public about your findings, you will be punished and silenced. If you give up your dreams without a fight and hand over your life's work to the authorities, you will be punished, but a little less. This is the current report on the Czech Republic's stance on clean energy and energy independence. Approved quietly, quickly, unconstitutionally, and effective immediately. So this video will be removed by law on June 30th, 2025. That's why I suggest you download and save it. One day when your grandkids ask why they have to learn Chinese in school instead of Czech, you can show them this. The damage? Priceless. The consequences will be terrible. My project, CINK Fusion, was too close. They know it. They know it would mean the end for them. A clean, safe, practically endless, waste-free, and non-radioactive energy source means taking politics out of it. No one will need them. The end of all superpowers and big companies. They won't have anything to offer anyone. And that's not their dream. That's the end of their dream life as it is now. That's why they set traps everywhere. The traps are empty, and their bad dream is starting to come true. So quickly and without planning, the government dusted off and updated the atomic law, especially the part about small, compact, eco-friendly, and safe fusion reactors, which I am working on. I registered the first one at the patent office last week. Unfortunately, it has errors in it on purpose. The really important stuff isn't there. And now you know why it never will be, thanks to Amendment Number 83, 2025's collection. 3 days after registering at the patent office, they changed and approved the control law. That's why you have to keep looking for what I've already found, and keep going in the wrong direction, down the dead-end road of uncontrollable tokamaks, which use more energy than they produce. They start with a tiny nuclear explosion, which is triggered by neutron radiation. You really don't want to be near that. Their operating temperature is over 150 million degrees Celsius. At these temperatures, matter turns into plasma, which is squeezed away from the reactor wall by incredibly strong magnets. But those magnets work at minus 300 degrees. And keeping minus 300 right next to 150 million degrees, that's also just a dream. But that one is officially approved. It's allowed. This is because no material on Earth can withstand the turbulent sea of charged particles in the form of hot plasma. That's why most tokamaks costing billions of dollars eventually burned up. I've created a solution where an outside magnetic field isn't needed. For what I've done, I'll keep it to myself. To keep working, I'll have to change my citizenship. The size of a tokamak is huge. The energy output is negative, and the costs are astronomical. And despite decades of brilliant work by scientists, this solution is still far from a commercial fusion power plant. This way of doing things, often called hot fusion, is a brute force method. It's an attempt to overcome one of the strongest forces in the universe, the electrical pushback between positively charged atomic cores. Imagine trying to push two strong magnets together by their north poles. They push back with incredible strength. Similarly, atomic cores fight hard against being pushed together. The hot fusion plan is to heat them up so crazily that their sheer speed will overcome this pushback and force them to crash and join. That's why projects like ITER in France are so huge. They are giant efforts to win a cosmic tug-of-war with nature's basic forces. The dream is beautiful, but the path is incredibly hard. So the question is this the only way? Do we always have to build bigger, hotter, and more expensive machines to unlock the atom's power? What if instead of trying to overpower the core with brute force, we found a gentler, more elegant way? What if there was a method that didn't need the heat of a star, but instead used the strange and wonderful rules of the quantum world? Here begins a different story, not about immense power, but about clever persuasion. A story that suggests a new path that is gentler, smaller, and potentially much more reachable. It's a path that makes us rethink everything we thought we knew about fusion. While the world's attention has been focused on the massive scale of hot fusion, a quieter revolution has been quietly brewing in labs all around the world. This field is known as low-energy nuclear reactions, or LENR. As the name suggests, it explores the idea of starting nuclear reactions at room temperature or close to it, without needing star-like conditions. For a long time, this field faced a lot of skepticism and was often dismissed as impossible because it seemed to break the known rules of nuclear physics. How could you overcome the huge repelling force between atomic nuclei without incredible heat and pressure? The idea seemed to go against everything in mainstream science, kind of like saying you could climb a mountain by just walking straight through it. The main difference between hot fusion and LENR is in the approach. Hot fusion is all about brute force. It's about smashing atoms together so hard they have no choice but to fuse. LENR, on the other hand, is about being gentle. It's not about smashing things, but about creating a very special, carefully designed environment, where nuclei are encouraged to interact in unusual ways. The key isn't heat, but the local atomic environment. LENR supporters believe that by putting fuel atoms like deuterium into a tightly packed crystal lattice of metal, like palladium or nickel, you can create unique quantum conditions. This organized, dense structure acts like a kind of catalyst, a nuclear matchmaker, helping the nuclei get closer than they normally could. Think of it like this. Trying to get two nuclei to meet in a gas, like plasma in a tokamak, is like trying to get two specific people to meet in the middle of a huge, busy city by just telling them to wander around at random. The chances they'll find each other are tiny. In the LENR approach, instead, you invite them to a small, well-organized party inside a house, the metal lattice. Here, their movement is limited, they're close together, and the environment itself can affect how they act, making it much more likely they'll interact. It's a shift from brute force to smart design, from chaos to coherence. This concept, often called cold fusion at first, has changed a lot over time. Researchers now know it's not just about soaking metal in heavy water. It's a complex dance of material science, quantum mechanics, and electromagnetism. The goal is to create a quantum coherent state inside the material where atoms and electrons don't act as individuals, but as a collective synchronized system. It's believed that in this highly ordered cooperative environment, the magic happens that lets nuclear reactions take place without the violence of extreme heat. It's a gentler, subtler way to unlock the power of the atom. To understand how LENR might work, we need to take a strange and wonderful journey into the world of quantum mechanics. In our everyday normal world, if you throw a ball at a solid wall, it bounces back. It never, ever goes through the wall. The wall represents an energy barrier that the ball just doesn't have enough energy to overcome. This is how we experience reality. But at the subatomic level, the rules are different. Particles like protons and electrons aren't just tiny solid balls, they also act like waves of probability. And these waves can do something that seems impossible. They can tunnel through energy barriers, even if they don't have enough energy to get over them. This is called quantum tunneling. Imagine you're standing in front of a very tall, steep hill. You want to get to the other side, but you don't have enough energy to climb all the way to the top. In the classical world, you're stuck. But in the quantum world, there's a small, non-zero chance that you could just appear on the other side, as if you teleported right through the hill. That's quantum tunneling. It's one of the most counterintuitive, yet experimentally proven principles of modern physics. This very phenomenon is what allows our sun to shine. Even at 15 million degrees, the protons in the sun's core don't technically have enough energy to overcome their repulsion and fuse. They succeed because quantum tunneling gives them a shortcut through the energy barrier. In the context of LNR, we call this key moment CINK. The name itself is meant to be evocative, like the sound of a key gently turning in a lock, or a soft knock that opens a door. It represents the moment a nucleus successfully tunnels through the repulsive barrier of another nucleus. We're not trying to smash the door down with a battering ram like in hot fusion. Instead, we're gently tickling the lock with the right quantum key until it opens. CINK is that moment of successful quantum tunneling, the point where the impossible becomes possible, and a nuclear reaction is initiated without the need for brute force. It's the heart of the CINK fusion concept. This tickling isn't random. The goal is to create conditions that dramatically increase the probability of tunneling. Imagine the energy barrier between two nuclei as a very thick, wide wall. Hot fusion tries to give particles enough energy to jump over it. LENR, and specifically the CINK fusion approach, aims to make the wall thinner and narrower, making it much easier for a particle to tunnel through. This is achieved by using modified materials and specific electromagnetic fields. This process isn't about overpowering the nucleus, it's about persuading it, about creating the perfect quantum environment where the nucleus decides to tunnel on its own. It's a deep shift from a battle of force to a dance of probabilities. The success of the CINK fusion process completely depends on how we prepare the fuel material. It's not as simple as just grabbing some metal off a shelf. It's a careful, multi-step process in materials science, much like a master chef preparing a delicate and complex dish, where every ingredient and every step is super important. The journey starts with picking a basic metal, usually nickel, which is known for being able to soak up a lot of hydrogen. But a simple block of nickel won't do the trick. The goal is to create a structure that is very organized and very porous at the nanoscale, making the surface area as big as possible where the nuclear action can happen. The process begins by making a very fine nickel powder with a very specific grain size. This powder then goes through a fancy layering technique. Using a method like chemical vapor deposition, incredibly thin layers of other elements are put onto the nickel nanoparticles, such as palladium or titanium. These layers aren't just random, they are designed to create special quantum effects at the edges between the different metals. This layered nanostructure is made to act like a superlattice, a kind of scaffolding that can hold deuterium atoms in very exact, energy-friendly spots. The whole structure is designed to be the perfect host for the fuel, a welcoming place for the nuclear reactions we want to happen. Once this complex nanopowder is made, it needs to be filled with its nuclear fuel, deuterium. Deuterium is a type of hydrogen, often called heavy hydrogen, and its center has one proton and one neutron. There's a lot of it, and it's easy to get from water. The filling process involves putting the nanopowder into a chamber and adding deuterium gas at specific pressures and temperatures. The tiny nickel particles with their specially made surfaces act like sponges, soaking up deuterium atoms deep into their crystal structure. The goal is to get a very high filling ratio, packing the lattice as densely as possible with deuterium, bringing the nuclei incredibly close together in an organized, quantum-coherent metal environment. This fuel wafer is the final product. It's a small, solid, and stable disk of material. It's not radioactive and is completely safe to handle. All the possible energy is locked deep inside the atomic structure, just waiting for the right signal to be set free. This preparation is a testament to modern nanotechnology. We are basically building a tiny nuclear reactor, atom by atom, creating a material with properties not found in nature. This careful, precise engineering of the fuel is the first and maybe the most important step to making CINK possible. It's this carefully prepared stage that sets the scene for the quantum drama that's about to unfold. Once we have our perfectly prepared fuel wafer filled with deuterium, the next step is to activate it. But, how do you talk to a nucleus? How do you encourage it to make the quantum leap of tunneling? The CINK fusion approach suggests a fascinating method which honestly is more like tuning a musical instrument than operating a power plant. The idea is that the entire fuel wafer, the metal lattice and the deuterium nuclei inside it, has a specific natural frequency. If you find this exact frequency and stimulate the material with it, you can dramatically increase the collective coherent oscillation of the deuterium nuclei, thereby massively increasing the likelihood of tunneling. This process of finding the right frequency is called QECHO, which stands for Quantum Energy Coherent Oscillation. It's a diagnostic process that essentially listens to the fuel wafer. A very weak swept electromagnetic signal is applied to the material. As the frequency of this signal changes, sensitive detectors monitor the material's response. At most frequencies, nothing happens. But when the input signal hits the material's natural resonant frequency, a distinct echo is heard. The material absorbs a tiny amount of energy and resonates with the signal, like a guitar string vibrating when you play its matching note nearby. This QECHO signal tells us the precise frequency needed for activation. Think of it like trying to break a crystal glass with your voice. You can randomly shout at it in all sorts of pitches and nothing will happen. But if you can sing at the glass's exact resonant frequency, the vibrations will build up until the glass shatters. The QECHO process is the scientific equivalent of finding that one perfect note. Each fuel wafer, due to tiny imperfections in its manufacturing, will have a slightly different resonant frequency. Therefore, each individual wafer must be individually tested and tuned to find its unique activation signal. This is a critical calibration step that ensures the subsequent activation process is as efficient as possible. Once the CINK frequency is identified, we have the key. We have the specific electromagnetic note that will make the deuterium nuclei dance in unison. This frequency is then used to generate a much stronger, tailored magnetic field pulse. This pulse is not designed to heat the material in the traditional sense. Instead, it's designed to pump energy directly into the collective quantum state of the deuterium nuclei, putting them into a state of high amplitude, coherent oscillation. It is this synchronized, energetic ripple within the metal lattice that dramatically shrinks the repulsive barrier between the nuclei, setting the stage for CINK to occur on a massive scale. With our fuel ready and the CINK frequency precisely figured out, we're finally ready for the main event activation. The fuel wafer is placed into a reaction chamber surrounded by electromagnetic coils. Then a strong, precisely shaped energy pulse, vibrating at the CINK frequency, is fired directly at the wafer. This is honestly the moment of truth. But here's the really cool part. The electromagnetic pulse doesn't heat the wafer to millions of degrees like in traditional fusion. Instead, it delivers energy to the coherent system of deuterium nuclei. They start to vibrate, quite violently, in perfect sync, straining against the limits of the nickel lattice. This collective motion greatly increases the chance that quantum tunneling, the CINK, will happen between neighboring deuterium nuclei. When two deuterium nuclei sync and combine, they form a helium-4 nucleus. In this change, a significant amount of nuclear binding energy is released, around 24 million electron volts per reaction. But unlike the harsh, high-energy neutron radiation you see in hot fusion, the CINK fusion process is thought to release this energy in a much more manageable form. Because the reaction happens within a dense collective quantum system, the metal lattice, the energy is immediately absorbed by the surrounding lattice. Instead of a high-energy particle flying off, the entire wafer vibrates and releases the energy as heat, or more specifically, as energetic lattice vibrations known as phonons. This change from nuclear energy directly to heat in a solid material is, frankly, revolutionary. It means we don't need huge, complex systems to handle dangerous radiation, or to change the energy of fast-moving particles. The fuel wafer heats itself up, and this heat, it can be used in a very normal and efficient way. The reaction chamber can be surrounded by a heat exchanger, a system of pipes filled with a liquid, like water, or maybe a special cooling liquid. As the liquid flows around the hot reaction chamber, it absorbs the heat and turns into high-pressure steam. This is a principle we've known for centuries, ever since the start of the Industrial Revolution, really. The high-pressure steam is then used for what steam does best. It spins a turbine. The spinning turbine is connected to a generator, and the generator makes electricity. It's a beautifully simple and direct path from a nuclear reaction to usable energy. The quantum CINK at the atomic level leads to vibrations in the solid wafer, which creates heat that makes steam, which spins a turbine, which generates electricity for our homes and industries. The quantum weirdness at the start of the chain is turned into clean, reliable electrical energy through tried-and-true engineering at the end. It really bridges the gap between the exotic world of quantum physics and the practical needs of our modern world. The real promise of any new energy source, honestly, is in its energy density, how much energy you can get from a certain amount of fuel. And that's where the numbers for CINK fusion become, well, truly astonishing. The fuel deuterium is taken from water. On average, about 1 in every 6,400 hydrogen atoms in seawater is a deuterium atom. This makes it an incredibly abundant resource, available to every country with a coastline. But you know, its abundance is only half the story. The energy locked within it is simply staggering. According to the theory behind this process, the complete fusion of just 1 gram of deuterium would release an amount of energy equal to burning about 24,000 liters of gasoline. Let that sink in for a moment. A single gram of fuel, a tiny amount you could easily hold on your fingertip, could produce the same energy as a small tanker truck full of gasoline. That's the power of E equals mc squared. Even though only a tiny fraction of mass is converted into energy in a nuclear reaction, the c squared part of the equation, that's the speed of light squared, is such a huge number that the resulting energy output is immense. This incredible energy density means a CINK fusion power plant would need tiny amounts of fuel compared to any existing energy source, whether it's coal, gas, or even traditional nuclear fission. The potential applications are as vast as the energy yield. A small, decentralized energy unit, perhaps the size of a shipping container, could potentially power an entire neighborhood or small town for years with just a few kilograms of fuel. For industrial uses, factories could have their own dedicated power sources, making them independent of the grid and immune to power outages. Transportation could be, frankly, revolutionary. Electric vehicles could be designed with small onboard CINK reactors, needing to refuel only once in a lifetime, effectively giving them unlimited range. The logistics of our entire energy infrastructure would be transformed. But perhaps most importantly, this energy is designed to be clean. The primary product of the deuterium-deuterium fusion reaction in this process is stable, non-radioactive helium-4, the same harmless gas we use to fill balloons. The process produces no greenhouse gases and no long-lived nuclear waste. The fuel wafer itself, once its energy is depleted, would be a small, solid, non-toxic piece of metal. This combination of extreme energy density and inherent safety and cleanliness is truly the holy grail of energy production. It represents a future where energy is not only abundant and cheap, but also fundamentally harmless to our planet's environment. If a technology like CINK fusion were to truly prove viable, it wouldn't just be about making our current energy systems better. It would mean a complete change in how we do things. The effects would be felt in every part of our lives. Right now, the way we make power is very centralized. We have these huge power plants, coal, gas, nuclear, that make electricity and send it through a big, complex, and honestly quite fragile network. This system isn't very good, with a lot of energy lost when it's moved, and it's really easy for big power outages to happen. CINK fusion, with its promise of small, safe, and easy-to-grow reactors, could make a future where energy is spread out and local. Imagine every home having its own little power unit in the basement, maybe the size of a furnace, that would give all the electricity and heat a home needs for decades without needing more fuel. This would create true energy independence. Communities could make their own small power grids, share energy locally, and become strong against problems in the national grid. Developing countries, which often don't have the money to build big power systems, could jump right to cheap, clean, and reliable local energy, unlocking huge economic and social possibilities. Having energy is super important for modern life, for clean water, for healthcare, for education, and this could make it available to everyone. The way the technology can be made bigger or smaller would also let it go into markets that are impossible for nuclear power right now. Think outside the grid. Long space missions could be powered by small CINK reactors, giving enough power for trips lasting decades to the outer planets and beyond. Science research stations in far-off places like Antarctica or at the bottom of the ocean could run forever without needing constant, risky fuel deliveries. Even everyday electronics could be completely changed. A laptop or a smartphone could have a tiny CINK power source inside, letting it work for years without needing to be charged. The very idea of charging a battery could honestly become a thing of the past. This idea paints a picture of a world free from the limits of not having enough energy. It's a future where clean water can be taken from the ocean in huge amounts, where vertical farms and cities can grow food for millions under artificial light, and where we have enough energy to actively take carbon out of our air, turning back the harm caused by climate change. It's not just about keeping the lights on, it's about giving a basic building block, plenty of clean energy, that is needed to solve many of humanity's other big problems. It shows a future that is not just lasting, but also rich and fair for everyone. The story of CINK fusion, and frankly all pioneering science, is ultimately a story of courage. It's about the courage to look at a problem that has puzzled the greatest minds for generations and ask, is there another way? The pursuit of hot fusion is a noble and brilliant endeavor, but its immense challenges have led some to believe it's the only path. Yet, history is filled with examples of breakthroughs that came from questioning the established way of thinking, from challenging known facts, and from the courage to explore ideas that initially seemed impossible. From Galileo challenging the Earth-centered model of the universe, to the Wright brothers proving that heavier-than-air flight was possible, progress has always been driven by a few brave souls who refuse to accept the limitations of their time. The field of low-energy nuclear reactions has faced a long and difficult road, marked by skepticism and controversy. Yet a dedicated community of scientists worldwide has persevered, driven by tantalizing experimental results and a belief that the quantum world holds secrets we have yet to unlock. Their work is a powerful reminder that science is not a collection of unchanging beliefs set in stone. It is a dynamic, evolving process of exploration, discovery, and revision. The most exciting phrase to hear in science, the one that announces new discoveries, is not eureka, but that's strange. It is in the anomalies, in the unexpected results, that the seeds of revolution are often found. Whether the CINK fusion model or another linear approach will ultimately succeed is a question that can only be answered by rigorous, open-minded, and repeatable experimentation. But its very existence is a vital inspiration. It encourages us to think outside the box, to connect disciplines, nanotechnology, quantum mechanics, electromagnetism, in new and creative ways. It shows us that solutions to our biggest challenges, like finding clean energy, may not come from simply building bigger and better versions of old ideas, but from a fundamental rethinking of the problem itself. This requires us to be both imaginative in our theories and relentlessly thorough in our experiments. As we stand here today, on the threshold of what could be a new energy era, the most important lessons are humility and hope. We must be humble enough to admit that we don't know everything about the universe, and that the quantum realm may still hold profound surprises for us. In the Czech Republic, questioning established ways and seeking new possibilities is now subject to the SUJB office. Applying takes years. The approval conditions are impossible to meet. And in the end, any result of your work is confiscated without compensation. The search for a new path of safe fusion is forbidden in the Czech Republic from July 1st, 2025. Information about fusion on the internet is censored. Information about its discovery is punishable. Who would they sell coal, gasoline, diesel, uranium to then? Don't believe those slogans about supporting innovation. It's just a clever trap.